Generative AI, well, especially large language models, it seems to be absolutely everywhere now. Crafting emails, summarizing documents.
Yeah, it really does feel a bit like magic sometimes.
It does, but, magic always has a price tag, right?
Yeah.
Okay, let's try and unpack this a bit. For organizations actually moving LLMs out of the lab and into like real production.
Right, beyond just experiments.
Exactly. Those costs that seemed tiny at first, they can suddenly spiral. We're talking real money here. It could be a few cents for, on-demand stuff, but it could also be over $20,000 a month just for hosting one LLM instance.
That's a huge range.
It is. So this deep dive is all about pulling back the curtain on the actual economics of LLMs. How are they priced? What are those sneaky hidden costs? And maybe most importantly, what are companies doing to try and optimize all this spending?
It's a really fascinating area because, look, LLMs are incredibly easy to get started with. The results you get for chatbots or data parsing, document summaries, they can be tremendous.
Oh, definitely.
But moving them into production, that needs a serious look at the development and operational costs. So yeah, we're going to break down the factors influencing these costs and explore how you can actually truly optimize your expenses.
Okay, let's start right there with the basics. How do these incredibly powerful models actually charge us for their intelligence? Well, it seems like there are maybe two main ways organizations are paying.
Exactly. Yeah, we really need to distinguish between two main classes. You've got your managed LLM providers on one side and then open source solutions on the other.
Okay, managed providers like OpenAI, Anthropic, those names.
Precisely. Their core pricing unit is something called the token.
Ah, tokens. Heard a lot about those.
Right. And it's the basic foundation, the conversion unit. Tokenization is just the process of converting text like your prompt into these numerical values the model can actually process.
Got it. Numbers for words, basically.
Sort of. But what's really crucial to understand is that tokens they aren't consistent. Not across different models, sometimes not even for the exact same prompt on the same model. They can be really short, like one character or maybe a whole word.
So it's more of an estimate.
It's best to think of token counts as approximations, yes. And these providers, they price their models based on things like parameter size, the input token context window, and the model's complexity. Typically, they charge per million tokens consumed, and that's for both input and output.
Both ways. Okay.
Yeah. So just to give you some examples from OpenAI, their latest model, GPT-4o, is around $5 per million input tokens and $15 for output. But the older GPT, the non-turbo version with a smaller context window, that's $30 for input and $60 for output.
Wow, that's a big difference just between their own models.
Huge difference. And then you have GPT 3.5 turbo, which is way cheaper, like 50 cents for input, $1.50 for output.
50 cents versus $30?
Yeah.
That's massive.
It really is. And Anthropic's Claude models have a similar structure. Their Haiku model is super cheap, like 0.25 per million input tokens. Sonnet is in the middle at $3. And Opus, their most powerful one, is $15 for input, $75 for output.
$75 for output.
Okay.
And these prices change, right?
Oh, constantly. OpenAI especially updates pricing pretty frequently as new models come out or they find optimizations. It's something you have to keep an eye on.
Right. So that's the managed side. What about open source?
So with open source LLMs, you don't have those management fees or the per token pricing, which sounds great.
That sounds free.
Well, not quite. You avoid the direct token cost, but you absolutely incur the underlying resource requirements and the infrastructure costs. You have to run it somewhere.
Ah, the compute costs.
Exactly. And just like the managed ones, these open source models come in different sizes, measured in parameters, millions or billions of them. And generally, more parameters mean higher speed and accuracy, but also higher infrastructure demands.
So it's definitely not just counting tokens then. What other things make using these LLMs more expensive?
That's a really important question because, there are several critical factors beyond just the sheer number of tokens.
Okay.
First is what you might call model complexity, or maybe think of it as the model's thought effort.
Thought effort. I like that.
Yeah. So more sophisticated models, ones with really complex architectures or just a massive number of parameters, going from maybe 7 billion to 300 billion parameters, or using things like mixture of experts
A
model.
mixture of experts. What's that?
Think of it like having several specialized mini models or experts inside the main model. Each one is good at a different kind of task. So when a query comes in, the model routes it to the most relevant expert or maybe a few of them. It's more efficient for certain things, but it's still complex.
Okay, so more complex architecture.
Right. All that requires higher computational demands, so higher costs. Put simply, the smarter, more capable models are just more expensive to run.
Makes sense.
Yeah.
What else?
Second, input size. Just the overall number of tokens you send to the model and that you get back from it. That directly impacts processing time and the resources needed. Larger inputs, larger outputs mean more power, higher costs. Pretty straightforward.
Okay, size matters.
Definitely. Third, the media type. If the model isn't just handling text, if it's processing audio or images or video.
Like DLE creating images.
Exactly. Or models that understand spoken language. Those demand significantly more resources. The data is just bigger and more complex to process, so cost goes up.
Right, more data, more processing.
And finally, latency requirements. How fast do you need that answer back?
Speed.
Yeah. If you need near-instant responses, that demands more computational resources ready to go or really highly optimized infrastructure. And that's just more expensive to build and maintain.
Okay, so complexity, size, media type, and speed. Got it.
Yeah.
So when an organization decides, okay, we're moving beyond experiments, let's put this into production, how do they actually set that up? How do they pay for it day to day?
Right. There are basically two main ways people approach this in production. First, you can host your own infrastructure.
Build it yourself, essentially.
Pretty much. Build and manage your own servers, either on your own premises or, more commonly, in the cloud. So, for instance, if you wanted to run a popular open source model like Llama 3, you might use something like an AWS ML.P40.24x large instance.
Okay, that sounds powerful and expensive.
It is. That instance costs almost $38 per hour.
Per hour. Ouch.
Yeah. So if you need that running 24/7, you're looking at over $27,000 a month just for one instance to host the model.
Wow. Okay. That gives you control, I guess, but that's a serious investment.
Huge investment, significant upfront cost and ongoing maintenance. Absolutely. So the alternative is the model as a service approach, SaaS.
Right, using the vendor's platform.
Yeah.
Like OpenAI's API.
Exactly. You use the LLMs provided by the AI vendors, usually on that paper token basis we talked about earlier. This way is generally more cost-effective, especially if you don't want the headache of managing infrastructure or if you're operating at a smaller scale.
Makes sense. And the cost difference there can be huge too, right? You mentioned the GPT-4 versus 3.5 example.
Immense. Yeah, that example of processing, say, 1 million input tokens and 1 million output tokens. With GPT-4, you're looking at maybe $90 total.
Right.
With GPT 3.5 Turbo, it's about $3.50.
$3.50 versus 90. Yeah, that really highlights how critical choosing the right model is. Not just the best, but the right one for the job and budget.
Absolutely critical. And just a quick note on language, sometimes using special characters or languages other than English can actually increase your token count and therefore your cost because of how the tokenization works differently. Something to be aware of.
Good point. Okay, so we've got managed versus open source, tokens, complexity, hosting, but I know a lot of teams get hit with what people call bill shock when they move to production. What are the costs that kind of sneak up on you, the less obvious ones?
Yes, bill shock. It's very real. And it happens because, honestly, it's not always straightforward to estimate these costs accurately. There are several hidden factors.
Like what?
Well, first, just the variable input and output sizes. You might design your application assuming average use, but user inputs and what the model generates back can vary wildly. One user asks a simple question, the next pastes in a huge document. That leads to unpredictable token counts.
Right, users are unpredictable.
Totally. Then there are hidden prompt costs. This one trips up a lot of people. Your application often includes system prompts, background instructions, context that gets added to every single request a user makes, silently.
Every time.
Every single time. It's adding tokens you might not even be tracking directly. There's a report, for instance, that the leaked system prod for GitHub Copilot was nearly 487 tokens long.
Whoa, almost 500 tokens just sitting there in the background.
Exactly. Before any code or user query was even added, imagine that multiplying across millions of requests.
Yeah, that adds up incredibly fast.
Yeah.
Okay, hidden prompts. What else?
Well, if you're using more advanced agent workflows, these LLMs might make background API calls themselves.
The LLM calls other APIs.
Sometimes, yeah. To implement certain reasoning frameworks, like something called React, or maybe to summarize chat history for memory buffers, each of those background calls costs tokens and adds latency.
Okay, agents making calls. That's sneaky too.
It can be. And finally, a big one recently is vector databases.
Right, for embeddings and search.
Exactly. You store these numerical representations, embeddings of your data, text, images, whatever. Creating those embeddings usually involves calling an LLM's embedding model, which costs money. And then searching those databases, especially for complex semantic search, uses more advanced, costly techniques. These costs are often significantly higher than basic text generation calls.
So setting up and querying those vector stores is another hidden cost center.
Definitely a common source of unexpected expenses.
Okay, so with all these factors, tokens, complexity, hosting, hidden prompts, background calls, vector databases, what can organizations actually do to get these costs under control? It feels like you're constantly juggling speed, cost, and how good the answer is. Like a game of whack-a-mole.
Huh, yeah. It can feel like that sometimes. But what's fascinating here is that there are actually several really effective strategies to manage these trade-offs.
Okay, good. What are they?
Well, the first, and maybe most obvious, is simply choosing the right LLM size. We've touched on this, but it bears repeating. Larger LLMs give you more accuracy, sure, but at a higher cost. You have to really consider the balance needed for your specific use case.
Do I really need the absolute top-of-the-line model for this task?
Exactly. Maybe a smaller, faster, cheaper model is perfectly adequate. Second, there's a technique called quantizing LLMs.
Quantizing, what does that mean?
It's a clever way to reduce the precision of the model's internal numbers, its weights. Think of it like slightly reducing the resolution of a digital photo. You make the file smaller and faster to load, often with very little noticeable difference in quality.
Okay, so smaller model, less compute.
Precisely. It leads to improved speed and uses fewer resources, often with only a slight, sometimes negligible drop in accuracy. Actually, there are cases where a quantized larger model, like a quantized Llama 2 13B, performed better than a smaller unquantized one, like Llama 2 7B, because it ran more efficiently even though it started bigger.
Interesting. So quantization is a key tool.
A very powerful one. Third, you can consider fine-tuning LLMs. This means taking a base model and training it further on your own specific data or tasks.
So you customize it.
Exactly. There's an upfront investment cost to do the fine-tuning, but it can make the model significantly more effective and efficient for your specific needs. This can potentially reduce your overall costs in the long run because it performs better with less prompting or on smaller models.
Okay, targeted training. Makes sense.
Fourth, and this is crucial, constructing better prompts, just writing clearer, more effective instructions for the LLM.
Prompt engineering.
Yeah, good prompt engineering improves accuracy, reduces those annoying hallucinations, and can save you from having to run the same query multiple times, which costs money. Techniques like chain of thought prompting, where you ask the model to explain its reasoning step by step, can lead to better answers.
Though that might make the input longer, right? More tokens.
It might, yes, so there's a trade-off there too.
Yep.
But often the improved accuracy is worth the slightly higher input costs because you avoid errors or needing reruns.
Got it. What else?
For tasks that aren't time sensitive, where you can wait maybe up to 24 hours for the result, many providers offer batch API discounts. Using these can cut your cost by 50%.
50% just by waiting.
If the task allows for it, yeah. It's a huge saving for things like large document processing overnight.
Definitely worth considering.
You can also think about leveraging specific thought process models. Some newer models, like one called O1 Preview, are designed for complex reasoning, sort of like agent as a service.
Agent as a service.
Yeah. They might be more expensive per call, but they can solve complex multi-step problems so efficiently that you end up needing fewer calls overall compared to stringing together multiple simpler model requests. So potentially cheaper in the long run for certain complex tasks.
Okay. Using specialized reasoning models.
And finally, back to media types, media processing optimization. If you're generating images, like with DALL-E, you have choices. DALL-E 3 gives higher quality but costs more, maybe 4 cents per image. DALL-E 2 is cheaper, 0s or 2 cents per image, but maybe slightly lower quality.
So you choose based on need versus budget.
Exactly. It's about making conscious, informed choices at every step of your LLM workflow: model size, quantization, prompts, batching, specialized models, media quality.
Oh, okay, that's a lot of levers to pull. But it sounds like managing costs is a constant battle. Is there any good news on the horizon?
Yes. While managing costs is definitely a challenge, there's an incredibly exciting counter trend happening, something that promises to open up entirely new possibilities. Have you heard about LLM-flation?
LLM-flation. No. What's that? Sounds like inflation, which is usually bad news.
It does sound like it, but it's actually the opposite. It refers to the rapid, really astonishing decline in the cost of LLM inference.
Inference meaning actually running the models, getting the answer.
Exactly. The cost of getting the model to think and generate a response. It's a trend very similar to what we saw historically with Moore's law for computing power or Edholm's law for network bandwidth.
Okay, costs going down fast. How fast?
Well, the big picture is kind of mind-blowing. For an LLM of equivalent performance, so comparing apples to apples in terms of capability, the cost is decreasing by roughly 10x every single year.
Wait. 10 times every year. That sounds almost unbelievable. How is that even possible given everything we just talked about with token costs and infrastructure?
It is staggering, isn't it? But let me give you some real-world numbers to back that up.
Please do.
Okay. When GPT-3 first became publicly available, back in November 2021, a model that scored around 42 on the MMLU benchmark, that's a standard academic test for overall LLM capability.
Okay, MMLU 42.
That capability cost about $60 per $1 million tokens back then.
$60. Got it.
Now, fast forward to November 2024. The cheapest model you could find that achieves that same MMLU 42 performance, something like Llama 3.23B run on a platform like Nalo. Together, .ai costs about 0.06 per million tokens.
6 cents. Down from $60.
6 cents. That is a 1,000-fold decrease in cost in just 3 years for the same level of performance.
1,000 times cheaper.
Yeah.
Wow. Okay, starting to see what you mean by LLM inflation.
And it's not just at the low end. For higher performance level, say an MMLU score of 83, which is closer to early GPT-4 level, the costs have dropped by a factor of 62 just since GPT-4 itself was released in March 2023.
So it's happening across the board for different capability levels.
Exactly. A massive deflationary trend in the cost of AI thought.
So why? How is this happening so fast?
It's really a powerful combination of factors all hitting at once. First, you've just got better cost performance from the hardware, the GPUs.
That gave faster chips.
Faster, more efficient chips. Then, huge advances in model quantization, like we discussed. Moving from 16-bit calculations down to 4-bit calculations makes the models much, much lighter and faster to run.
Right. Less compute needed.
Then there are continuous software optimizations, smarter ways to write the code that runs these models, reducing how much compute and memory bandwidth they need. Also, critically, we're seeing smaller models achieve higher performance.
Smaller but smarter.
You got it. A model with maybe only 1 billion parameters today can actually outperform a massive 175 billion parameter model from just 3 years ago. That's a huge efficiency gain.
Incredible.
Plus, there are much better instruction tuning techniques, ways to train the models to better understand and follow human instructions using methods like RLHF reinforcement, learning from human feedback and DPO, direct preference optimization. They just get better at doing what you ask them to do more efficiently.
So better training makes them more efficient too.
And finally, a huge driver is the rise of open source models. Companies like Meta releasing Llama, Mistral releasing their models. This injects massive competition into the market.
Competition drives down prices.
Always does. It puts pressure on the commercial providers and reduces profit margins across the whole value chain, from hardware to hosting.
Okay, so hardware, quantization, software, smaller models, better training, and open source competition. That's quite a convergence.
It really is. So what here is enormous? Think about it. Every time the cost of a fundamental technology like this drops by an order of magnitude by 10x, it unlocks entirely new use cases, things that were maybe technically possible before, but just way too expensive to be practical or commercially viable.
Like what? Give me an example.
Okay, imagine processing, say, 10 hours a day of human speech, maybe for transcription or analysis, for an entire year using a GPT-3 class LLM. That would now cost you about $2.
$2 for a year's worth of continuous speech processing.
Roughly, yeah. Or consider the entire Linux kernel, that's about 40 million lines of code, processing all of that through an LLM, probably less than $1 now.
Under $1.
Building a simple voice assistant for an application. From an inference cost perspective, it's basically free now. The game has completely changed for what's economically feasible.
Wow. Okay, LLM inflation is definitely the good news story here. But bringing it back to the companies trying to use this stuff. We've talked about the cost factors, the hidden costs, individual optimization tricks like quantization or batching. How do you actually put all that together? How does a company figure out, okay, for this specific task, should I use quantized model A or fine-tuned model B, or maybe write it to cheap model C first? Seems really complex to make that decision optimally every time.
That is precisely the multi-million-dollar question, isn't it? Predicting which specific optimization technique or which model will be the most effective for a given input before you run it. That's incredibly difficult.
Yeah, feels like guesswork sometimes.
Which is exactly why you need a more analytical, data-driven approach. Relying on intuition or simple rules of thumb often won't cut it if you really want to maximize savings while maintaining quality.
So are there systems or frameworks emerging to help with this?
Yes, absolutely. And this is where things get really interesting, moving beyond individual tricks to holistic optimization systems. Let's talk about a framework called QC-Opt as an example.
QC-Opt, what's that stand for?
It stands for Quality Aware, Cost Optimized LLM Routing Engine.
Quality Aware, Cost Optimized.
Okay.
Sounds promising. What's the core idea?
So QC-Opt focuses on basically three main components working together to optimize how you use LLMs, specifically aiming to slash costs while making sure the output quality stays high or even improves.
Okay, component one.
Component one is about estimating model performance without actually calling the model.
Predicting performance beforehand.
That's the critical challenge, right? If you have, say, 5 different LLMs available, and you have to query all 5 just to see which one gives the best summary for a particular document, you've already spent 5x the cost and added a ton of latency just figuring out what to do.
Yeah, defeats the purpose of saving money.
Exactly. So QC-Opt uses a clever approach. They trained a specialized AI model, technically. It's a BERT model backbone with a regressor head on top, trained on lots of data.
Okay, a predictor model.
Yeah, a BERT score predictor. This predictor model learned to estimate the likely output quality of various different LLMs for a specific task, like document summarization, just by looking at the input document. It predicts the quality without having to actually run the expensive LLMs at inference time.
So it's like a quick, cheap pre-check.
Precisely, a smart pre-flight check. And they've validated this predictor through user studies, showing it correlated well with what humans thought about the quality, especially when there was a clear performance difference between the potential LLMs.
Okay, that's clever. Predict performance without spending the money. What's component two?
Component 2 is the smart router for optimizing LLM selection.
The router decides where the request goes.
Exactly. Once the predictor gives its quality estimates for the available LLMs, the smart router takes over. It uses a sophisticated budget-aware optimization algorithm.
Budget-aware. Okay.
This algorithm considers the predicted quality from step 1, the actual costs of each LLM, their input-output token costs, any fixed invocation fees, and also any latency requirements you might have.
So it juggles quality, cost, and speed.
Right. The underlying math problem of picking the absolute best sequence of models under budget and latency constraints is actually really complex. It's NP hard, mathematically speaking. But QC-Opt uses smart algorithms like LP rounding techniques to find very efficient near-optimal solutions quickly.
Okay, so it does the complex math for you.
Essentially, yes. And crucially, it recognizes something important. The biggest, most expensive model isn't always the best performer for every single task or even every part of a document.
So it might route different parts of a long document to different models.
It can, yes. It might decide a cheaper model is perfectly fine for summarizing Section 1, but a more powerful one is needed for the complex analysis in Section 3. It makes granular, context-aware decisions to meet your quality target at the lowest possible cost.
It's really smart, like an AI traffic controller for LLM requests, factoring in tolls and speed limits.
That's a great analogy. Okay, so that's predicting performance and smart routing. What's the third component? The third key piece is actively reducing the input token count using a token optimization module.
Making the input smaller before sending it.
Exactly, because beyond just picking the right model, making the input shorter directly costs fewer input tokens, and it also helps make sure your content actually fits within the model's context window limit.
Right. Context windows are still a limitation. How does it reduce tokens?
It uses a couple of techniques. One is token-optimized text simplification. This involves automatically rewriting sentences to be simpler and shorter, while trying hard to preserve the original meaning and aiming for a specific target token count reduction.
like finding synonyms or rephrasing.
Yeah. The example they gave was changing archaeological evidence suggests a history of settlement in the area since roughly 2000 BC. To the shorter, archaeological evidence shows settlement in the area since 2000 BC. Fewer tokens, same core meaning.
Okay, automated simplification.
Then it also uses a set of token optimization heuristics. These are like general editing rules applied automatically to reduce tokens while maintaining quality.
What kind of rules?
Things like adjusting spaces and capitalization, replacing longer synonyms with shorter ones, lemmatization, reducing words to their root form, removing unnecessary brackets or punctuation, handling compound words efficiently, sometimes selectively removing common stop words like the or a if appropriate, handling acronyms smartly.
A whole toolkit of text shrinking tricks.
Pretty much. And what's really neat is that the system can even optimize how aggressively it applies these rules. It can treat it like a classic optimization problem. The knapsack problem.
The knapsack problem, like packing a bag.
Exactly. You want to pack the most valuable items, save the most tokens, without exceeding the bag's capacity, losing too much quality. So it finds the best balance between token reduction and potential quality impact for your specific needs.
Wow. So QC-opt combines predicting quality, smart routing based on cost and latency, A&D automatically shrinking the input text. That sounds comprehensive.
It is. It's a really holistic approach, and the results they reported were pretty striking.
What did they find? Did it actually work?
Yeah, their experiments show the QC-opt framework achieved cost reductions in the range of 40% to 90% compared to simpler approaches.
40 to 90% reduction. That's huge.
Massive savings. And interestingly, in some cases, it actually improved the observed output quality by 4% to 7% at the same time.
Improved quality while cutting cost.
Probably by being smarter about routing requests to the model that was genuinely best suited for that specific input, rather than just defaulting to the biggest model or a naive cascade. When they compared QC-opt directly to things like sequential LLM cascades, where you might try a cheap model first, then a medium one, then an expensive one.
Yeah, a common strategy.
QC-opt achieved the same level of quality, but at significantly lower costs. It really demonstrates a more intelligent way to orchestrate LLM usage.
Okay, that QC-opt example really drives home how sophisticated cost optimization is becoming. It's not just about picking a cheaper model. It's about intelligent dynamic management.
Absolutely. It's moving towards real-time, data-driven optimization.
So we've really covered a lot of ground here. We've gone from the basics of token pricing all the way to these advanced optimization frameworks. It feels like we've done a true deep dive into the dollars and cents of LLMs.
Indeed. From the micro cost of a single token to the macro cost of infrastructure, and now these incredibly clever ways to manage it all. It really highlights that LLMs are groundbreaking, powerful technology, but maybe like high-performance race cars.
Yeah. How so?
Well, they're incredibly capable, but you probably wouldn't use one just to pop down to the grocery store if a smaller, more efficient vehicle will do the job perfectly well.
Right. Using the right tool or the right engine for the task.
Exactly. That balance between performance, cost, and accuracy is just so crucial. Understanding all these factors we've talked about is absolutely vital for deploying LLMs effectively and actually getting value out of them.
So wrapping this up, what's the big takeaway for everyone listening?
I think there are two key things. First, that LLM inflation trend, the rapid ongoing decline in inference costs, is a massive tailwind for AI adoption. It's genuinely opening up possibilities that were unthinkable even a year or two ago.
Making AI more accessible across the board.
Definitely. But second, alongside that, the innovation in optimization methods, like that QC-opt framework, is ensuring that we can use these increasingly powerful tools much more judiciously and efficiently. We're getting smarter about how we spend our AI budget.
So costs are falling, and our ability to manage those costs is improving. That sounds like a recipe for, well, a lot more AI in the future.
I think that's a safe bet.
So maybe the final thought for you, the listener, is this. As these LLM costs continue to plummet and the optimization techniques get even more sophisticated, what new applications, what new ideas will suddenly become not just technically possible, but truly commercially viable for your projects, your business, or even just your own creative pursuits? Something to mull over until our next deep dive.